So Newton, as you guys might know, came up with three Newton's laws, and there's actually a fourth one, Newton's law of gravitation, but we won't talk about that. Among the three laws, the most important is probably what's the first one? The first one. Right, that's an important one, yes. Do you remember what it says? Yes, right. So the first law is like an object in motion will stay in motion. If I throw this pen and there's no friction whatsoever, it's just going to keep going forever. But unfortunately, there is friction and other stuff acting on it, so it doesn't do that. But more importantly, today, we'll be talking about Newton's second law, which is, as some of you might have heard, like F equals ma, maybe somewhere, no. So this is Newton's second law. Is F equals m mass times acceleration, right? So if I tell you what are all the forces that are acting on the particle, I draw these crazy diagrams and say, oh, let's say there's a force here from me like pushing on it or something, and I add them up, I can set it equal to mass times acceleration, and that in turn will basically let me know the equations of motion of the particle. Now, in mechanics, the most important thing you care about is the particle's equation of motion, right? You're trying to figure out how things move around. So if I can just give you an equation like, say, x is a function of t, meaning the x being the position of the particle, if I can somehow give you an equation describing the position of the particle as it goes through time, then I will have solved mechanics for this particular particle. Right? And so Newtonian mechanics allows us to easily do that by just drawing this what's called a free body diagram and solving for what acceleration is like acting on the particle, right? It turns out there are two other completely equivalent ways of formulating mechanics. So there's also something called Lagrangian mechanics. Lagrangian mechanics, which is what we'll be mainly dealing with today. And there's also something else called Hamiltonian mechanics. And these were actually later discovered by people and formulated by a bunch of Lagrange and Hamilton. And it turns out it's a completely equivalent way of doing things with mechanics. Now you might wonder, like, why would we want to do this? Right? If we have a perfectly good way of figuring out how things move around using Newtonian mechanics, why would we ever want to care about something called Hamiltonian mechanics or Lagrangian mechanics? Right? Well, just like how you can have a wrench and like a screwdriver, they all help you fix things. They sort of give you different advantages, pros and cons, right? So, for example, in this case with Newtonian mechanics, it's like so tedious to have to figure out, oh, what are all the forces acting on it? Like, let's say I give you something that's much bigger. Like, it's not just a point particle, but it's actually like, say, a ladder. This pen's kind of dying. I'm gonna switch to one of my own. Yeah. So let's say I gave you a ladder. It looks something like this, right? And it's leaning against the wall. This is the wall. Here's the ground. Right? And here's some angle between the ladder and the wall. Now I'll ask you, what are all the forces acting on this ladder, and you might say, okay, sure, let me slowly work this out for you. I'll have some force acting this way up, pushing it, preventing it from like just falling down. There's some force from the wall coming this way, and then there's a bunch of like internal like forces between particles within the ladder, and you'll be like, oh, this is like really really hard, and I don't really want to figure out how to draw all these random forces. So and fair. That's fair, because that's tedious work that you don't want to work out, drawing all these forces. Now, that's where Lagrangian mechanics comes in. With Lagrangian mechanics, actually, with Lagrangian mechanics, it's easier in the sense that you don't have to figure out what are all these forces acting on your particle. All you have to do is write down its kinetic energy and its potential energy. Does everyone know what kinetic and potential energy are? Okay. Oh, by the way, if you guys if I ever say anything that you guys don't quite understand, feel free to just raise your hand and ask me, because I'm here to make sure you guys understand what I'm talking about, and it's sort of useless for you guys if I'm just talking and talking and talking. Okay, so let's erase this. We won't be dealing with this today. We'll be dealing with this. So let me ask you guys something. If I take this, okay, and I toss it in the air, like this, between let's say point A is the starting point and point B is the ending point. Okay, I start here, I toss it, and it comes back down. Sorry, I didn't catch it, but pretend I did. So what's to prevent this pen or this marker from doing some crazy path that I don't expect it to? Like, what's gravity? Sure, yes, that's one way of looking at it. Correct. Like energy. Yeah, that's also a good way of looking at it. What do you mean by direction? So these are all like these are like what we expect the marker to behave like intuitively. Right? We don't expect the particle to go like, or for the marker to go from here. I throw it up, and then it hovers here for like 10 seconds and falls back down again. Or you don't expect it to go like this and all over the place and comes back down. Now, you can look at it from all those perspectives, like, oh, there's only this force acting on it. So there's only gravity acting on it. So it has to, either fall up or fall down. Gravity acts downwards, its direction, so it has to go down. There's another way of looking at it that comes from Lagrangian mechanics, which I think is actually an incredibly beautiful but abstract way of thinking about why things move in the way they do. And that principle is called Hamilton's principle. Hamilton principle. Let's plot this out. Let's plot out what we expect. Something that's like this, that's only acting on gravity. Let's plot out how we expect it to move, right? If this is time, let's call that t. And if this is the position as a function of time, x of t, if you started out here at point A and all this point B, you'd expect for it to go something like this. This is just in one dimension, but because time is progressing this way, it looks like this. So it's going up, and it comes back down again, right? And as we said, we don't expect for it to go like, oh, it'll instantly go up in the air and hover for a little bit, and then fall back down. Right? We don't expect that to happen. And one alternative explanation is with Hamilton's principle, which says that the true path, the true trajectory of a particle is the one that extremizes the action. Okay. This is all some gibberish to you, and I'm supposed to explain what all this means. So the true trajectory, meaning the actual path it takes, not the imaginary path that we ask ourselves why it couldn't take. So let's call that x star. This would be x star. The true trajectory of a particle is the one that extremizes the action. So if you guys, so since you guys haven't taken calculus yet, I'll sort of give an intuitive explanation of what extremizes means. Like, for example, if this were just in one dimension or 2 dimensions, and you had some graph, right, and that looks like this, for example, then this point would be an extremal point, and this point would be an extremal point. Right? It's a local minimum or a local maximum. Right? Locally, it's like around. Locally meaning around this area, it's greater than all the other ones. And local minimum means around this area, it's lower than all the other ones. So that's one example of an extremal point, but it doesn't necessarily have to be this way. So formally, an extremal point just means that the first derivative is equal to 0. But for example, it doesn't necessarily have to look something like that. Turns out the graph, like say f of x equals x cubed, it looks something like this. Right? When the derivative is 0, it just means that the slope of the graph at that point is basically 0. So if you see the slope at this point flat, so it's 0 because flat lines have 0 slope, and same with here. Derivative. So you guys have seen like slopes before, right? So like for example, the slope of a line is like y equals like the m in the y equals mx plus b, right? So slope, it's like rise, change in y over change in x. This is like, let's call this change in y. Call this change in x. Delta just means change. So you can think about it as if this were a line, then this would be the slope of, it'd be the slope of the line would be delta y over delta x. Now let's say I have some other graph that looks like this that's not a line, and I zoom in very, very close to like this one point, okay? And it's approximately a line, right? It'll look like I can draw a line tangent to it, and it'll look approximately like the line, and the derivative is the slope of the graph at that point when you approximate it by a tangent line. So that's why I say, at this point and this point, for example, these are what are known as extremal points because their slopes are 0. They're completely flat. Okay, so what is action? Now, action is this. It's actually a mathematical quantity that physicists defined, and the action they represent it by the letter S, which does not stand. Which for some reason S means action. Right? It's just the convention that people start with. S is actually equal to what's known as an integral, which I don't expect you guys to know what that means. From time 1 to time 2 of a function called the Lagrangian, which is a function of x and velocity, position of velocity, and time, dt. So what is an integral? You can think about an integral as just a sum of the area under a curve, right? So if this is my function L, let's say it looks like this. This is L of x, and this is x, and this is, say, x1, x2, then the integral of this function is area between the curve. So it's all this stuff, right? So the reason I say it's like a sum is because you can cut this down into like tiny like rectangles, right? Like you can approximate it like this, and then make the width of the rectangle smaller and smaller, and that will give you a better and better approximation to the area under this curve. So that's what's known as an integral, and the action is this quantity. It's the area under this weird function called the Lagrangian. So the true trajectory of a particle is the one that makes this integral the smallest possible. Because nature is very, very lazy, and it likes to minimize things whenever it can. It doesn't want to have too much energy, because that's why boulders roll down from the top of the hill. It's because it's trying to minimize the amount of energy that it has. And that is also why light travels in like straight paths, because light likes to take the path that it can travel in the shortest amount of time. So here we're not actually too surprised that there is some other quantity behind the scenes that nature is trying to minimize when it determines how things are going to move. And this is one example of such a minimization that nature does. So this is all, oh, sorry, I forgot to define what the Lagrangian was. The Lagrangian, is, noted by L, is actually the difference between the kinetic energy, let's say K, minus the potential energy of your particle. So the kinetic energy of your particle, as some of you might know, is 1/2 mv squared. Right? It's the where v is the velocity of the particle. So the faster it's going, the more kinetic energy it has, and the more mass it has, the more kinetic energy it has. Like a truck, going like blazing down the highway, is going to have much more kinetic energy than a little pen, and I'm going to threw it across the room. So this is what K is the kinetic energy, and it's the difference of the kinetic energy with the potential energy. So the potential energy, does everyone know what potential energy is? Huh? Voltage? Not quite. So you can think about it like potential energy. Like let's say I'm on a hill, okay? And potential. Oh, okay. What do you use? Yeah, that's right. What do you usually use for potential energy? P? Okay, we could do that. That makes it clearer. P. So you can think about potential energy as like energy stored in the particle that's waiting to be used. So for example, if I'm on a hill, say this is me, I can if I just step this way a little bit, I'm gonna fall down a hill, right? I'm gonna tumble and like roll my way all the way down here, and hopefully I'll survive. Maybe a little bit sad, but it takes energy, right, to make me go faster and faster and roll down a hill. So you can think about it as me having some more amount of potential energy when I'm up here than when I'm down here, right? Because where can I roll when I'm at the minimum? I can't really go anywhere. But here I have the potential to roll down a hill, and it's sort of energy that is stored within me when I'm up there. So for a normal particle, like just a point particle, the potential energy for it is mass times g, which is the like acceleration due to gravity, times, because we're working in one dimension, it's x, where x is the height of the particle relative to something. So for example, let's say I weighed like 100 kilograms, and I am like 10 meters above the ground when I'm up here, then my potential energy would be my mass times g times x, which is equal to 100 kilograms times g, which is like 9.8. Yep, that's correct. 9.8 meters per second squared times 100 times 10 meters. And that's about 9,800 joules. So joules is just a unit of measurement. So that's what potential energy is. And if you write down what's the kinetic energy of your particle and what's the potential energy of the particle, it turns out that you can derive a set of equations using Hamilton's principle that exactly reproduces what you would have gotten if you had used Newtonian mechanics instead of Lagrangian mechanics. And that equation is called the Euler-Lagrange equation. Write the name. Euler-Lagrange equation. And the reason it's equations is because in general, if you're working in like n dimensions, there will be n sets of the same equation. Well, n sets of equations of similar form, and they'll all look something like this. I know all of you guys probably won't understand what this is saying, but it's sort of pretty to just see it for once. This. It is a partial derivative. This is a partial derivative. Let me just finish writing this down. Partial L, partial x, I equals 0. So dot is just is the time derivative of x, which is physicist notation. But since you guys have not seen calculus before, there's not really an easy way for me to give you an intuitive explanation of this equation, unfortunately. I was going to do an example of using this equation, but that also would require calculus. Sorry, I'm not like trying to I'm not trying to like scare you guys or anything, but it's just like calculus is a very, very natural language for physics, huh? Yeah, it's like the most important thing you'll ever learn for physics. Like it's calculus. Like everything will use it, and engineering too if you're interested in that. Yes, yeah. You learn calculus, yeah, or some like after like algebra 2 and trigonometry, and you'll learn it. Um, so unfortunately, I cannot do that example. Let me see what I can uh, talk about. So if you knew calculus, you could take your L that you just wrote down and plug it into here, and you would basically reproduce the equations of motion of your particle. The equation of motion is what I mentioned earlier, meaning it's it's how the particle is going to behave and move around. The equation of motion. So d is derivative. So d dt is a derivative with respect to time. Yeah, x is position. Yes, that's correct. Um, so if you were to do this, you would get some equation. If you were to plug in this L into here, you would get basically this equation: m a equals minus mg, and this is exactly what you would have gotten if you plugged in, your thing for F equals ma Newton's second law. But after doing all this, we spent like half an hour talking about all this other, Lagrangian mechanics. You might be a little bit surprised to see that, oh, it just gives you the same stuff you would have gotten anyway, and you might wonder, what good is this? Why would we want to waste so much time learning calculus and all that just to do this? Well, going back to my example of the ladder against the wall, it turns out that if you were to try to do it this way, with all the figure out all the forces, it would take you a lot of work. So if you come to Cornell and study physics, it's actually one of the problems is time for homework, and I think the answer is like 1 page or so, 1 or 2 pages of work, just to figure out what the heck this ladder is going to be doing, as gravity pulls it down. Um, yeah, I do. Yeah, I love physics very much. Yeah, yeah. It's a lot of work, but I think as you grow up a little bit, you sort of figure out what you enjoy. And some people, they prefer writing papers, and maybe like they like writing like 20 pages of paper or something, like instead of working on this. But yeah, yeah. I remember I was in earth science actually. Are you an eighth grader? Ninth grader, yeah. Did you guys have to do like weather maps and all that? Yeah, you guys are all from New York, right? So it's like part of the New York curriculum where you had to like draw the weather maps and all that. That was so terrible. I remember doing that. Yeah, and I don't remember a single thing about like weather anymore. I don't know. Yeah. Mhm. 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 So I guess one thing I didn't ask you guys when I was starting out, which I probably should have, is like, what are your interests? What are you most interested in, like in terms of like subject matter? Math, science? Okay. 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 And you? That's okay. Some people like. I'm surprised no one said like, oh, I love I love reading, or like I love writing. I love writing like novels or something, stories. No. Yeah, I mean, I think that there's a selection bias in there. Like people who come to physics class probably enjoy science more. I did, yeah. I loved reading when I was a kid, for sure. I mean, I still love reading, but I just don't have the time for it, unfortunately. You'll see that as you get older, the less time you'll have, and you know, they say that you won't. You basically just you get less and less time and want to do whatever you want to. So enjoy it while you can. But going back to all of this, now that I sort of got to know yourself, got to know you guys a little bit more, um, I won't write down any more formulas just so like I won't like bore you guys. But if after class or something, you want me to go into more details, I can definitely do that for you. Who here has heard of quantum mechanics? One person, two, Omar in the back. Anyone else? No? Quantum mechanics? Like Schrodinger's cat, all that? No? Okay. No, but that's related. That's like particle physics, and particle physics uses a lot of quantum mechanics. Let's talk about quantum mechanics and how all of this, this boring stuff, relates to the cooler and more abstract and counterintuitive notions of quantum mechanics. So it turns out that quantum mechanics, for those of you who don't know, is it's basically mechanics for very, very small particles. It describes the very, very small world, at like 10 to the minus 10 meters, at like the length scale sizes of like an atom. When things get down to that small, they no longer behave in this way, like in the way that we would expect them to in a classical world. And that's why we were working with classical mechanics in the beginning of the class, and now we're going to transition into quantum mechanics. Now, essentially, we're going from the very big things to the very small things, is what I'm trying to say. There are two main ways of approaching quantum mechanics from Lagrangian mechanics. Approaching quantum mechanics from classical mechanics. And both of them involve the two types of mechanics that I mentioned earlier, Lagrangian and Hamiltonian mechanics. Usually, for the first time, people see it with from the Hamiltonian mechanics perspective. But actually, you can go directly from this path, this idea of what path will a particle take, and go take that directly to quantum mechanics. So the weird thing about quantum mechanics is the following. Let's say I also, have some particle at some point. I want to ask what path is it going to take from point A to point B. Now, naively, you might say, oh yeah, just the same old classical path that it would take. Let's say, I threw it up, it would go like something like this. Naively, you would think that because that's what we're used to. Like, that's what our physical intuition is going to say. It's going to go up and come down. Well, if you said that, you would be wrong, unfortunately. In quantum mechanics, things not only can move in one path, they can move in any single possible path that it can take to go from point A to point B. And it does, in fact, take every single possible path from point A to point B. It can go like this, it can go like this, it can go up here, wander a little bit, come back. It can do all of these things. It can take every single possible path, and it does take every single possible path. Now the question is, how do we deal with this, right? How do we even come up with a notion of the path that a particle takes between one point and another, if it can go any old way that you just draw on the board. Well, the answer is, in quantum mechanics, you talk about probabilities. You talk about what's the probability of a particle going from here to here. And it turns out that the probability of a particle to go from A to B is roughly, I'll draw a squiggle here instead of an equals because it's roughly, comes from a sum over all paths of this thing called complex exponential e to the I action over h bar. H bar is some constant. I don't remember exactly what it is. It's like something times 10 to the minus 34. Huh? 1.05? Okay. So it's like h bar is like some number that's like approximately 1.05 times 10 to the minus 34. So basically, in quantum mechanics, we no longer deal with exact paths between point A and point B. Instead, you deal with infinitely many paths, and this is actually an infinite sum over infinite paths that it can take, which is a crazy notion because, like, in physics, we generally don't like to deal with infinities. Like you would only deal with infinities when your theory is wrong, because things don't have infinite energy. Otherwise, they would blow up, and you just don't have infinities in it. But in this case, this is where you actually do have infinities in physics. And you talk about, as I said, you talk about what's the probability of going from A to B. It's roughly the sum over all the paths, each weighted by this S from classical mechanics, this action here, divided by h bar. So this is just a way of me trying to explain to you just how closely related classical mechanics and quantum mechanics are, but also how completely counterintuitive quantum mechanics can be. And I'm sure that if you actually get there someday, and learn about quantum mechanics, you definitely will not see this until first year of graduate school, probably, for physics. So this is some really, really high energy. Huh? Oh, how do I know? Well, I took a graduate quantum mechanics course last semester, so that's how I know. But I'm a sophomore. Yeah. So this is like things that you probably won't hear about until very, very later on. In the case that any of you have heard of Richard Feynman, I don't know, has anyone here heard of Richard Feynman? No? Maybe? Okay. He is one of the most well-known geniuses of physics, and this notion of path integral was actually one of his. I'll just write his name here for more immortalization purposes. Richard Feynman, path integral. That's what they're called because, as I said, integral is like an infinite sum, and here you are summing over all paths, so the name path integral comes in. In case you guys are looking for like fun like biographies to read or something, Richard Feynman is a really, really interesting character. He taught at Caltech and later parts of his life. Sorry. He would, back when he worked on a Manhattan project, he would go into his coworkers' locks and like pick them actually, and take out all the secrets like the nuclear bomb and all that, and then trick his coworkers into thinking that the Soviets, the Russians, came in and like took all our American nuclear bomb secrets. But he was a fun guy, and he was a genius. In his spare time, he liked to play like bongo drums and all that, which is not what you expect, that a physicist would do. He like go to like bars and stuff and start playing. Oh, a bongo drum is like, it's like, it looks something like this. Right? Like a set of bongo drums, maybe like connected or something. Yeah, and then he would just like go to like bars and stuff and start playing his bongo drum. So he's a very, very interesting person. So probably the most interesting physicist ever lived. If you guys want to know more about biography.